Hello there, and welcome to Sleep Orion. Tonight, we journey back to July 20th, 1969, to a moment that would reshape human history. Not through grand speeches or sweeping vistas, but through the quiet, technical language of numbers and codes. Through voices crackling across the void. Through men and machines working in perfect, fragile harmony. We're going to read the transcript of the Apollo 11 lunar descent. Word by word. Number by number. We will follow Neil Armstrong and Buzz Aldrin as they guide the lunar module Eagle toward the surface of the moon, listening to every altitude call-out, every alarm, every heartbeat of uncertainty captured in those 13 minutes that changed everything. This is not a story of poetry. It is a story of precision. Of human beings trusting machines, and machines trusting human beings. Of split-second decisions made in the cold silence of space, where hesitation means death and courage means doing the math correctly under unimaginable pressure. Before we begin, if you enjoy these quiet journeys through history, I invite you to like, subscribe, or leave a thought in the comments below. It helps others find their way here, one curious mind at a time. For now, settle in. Let your breathing slow. And let us descend together toward the sea of tranquility, guided only by the voices of those who dare to go first. Let's begin. The journey to this moment began 96 hours earlier, on the morning of July 16, 1969, when the Saturn V rocket lifted from Launch Complex 39A at Kennedy Space Center in Florida. It was a Wednesday morning, humid and warm, with 1 million people lining the beaches and causeways to watch. 3 men sat in the tiny command module perched atop that towering rocket, atop 7.5 million pounds of thrust that would, in moments, transform fuel into fire, into velocity, into history. Neil Armstrong was the mission commander, 38 years old, a former Navy test pilot who had flown the X-15 rocket plane to the edge of space, who had commanded Gemini 8 and saved that mission from a thruster malfunction that nearly killed him. He was known for his ice-cold composure under pressure, for a mind that moved through problems with mathematical precision, for a voice that never wavered even when death was seconds away. He spoke rarely, chose his words carefully, and when he did speak, people listened. Buzz Aldrin was the lunar module pilot, 39 years old, a West Point graduate who had flown combat missions over Korea, who had earned a doctorate from MIT writing a dissertation on orbital rendezvous mechanics that would become the foundation for how spacecraft meet in space. He was brilliant, intense, deeply religious, and driven by a need to achieve, to prove himself, to be remembered. He would be the second human to step onto the moon, a fact that would both honor and haunt him for the rest of his life. Michael Collins was the command module pilot, 38 years old, an Air Force test pilot who had flown Gemini 10, who would remain in lunar orbit while his crewmates descended to the surface. He would be alone for 27 hours, circling a world where no human had walked, cut off from radio contact half the time, ready to return home alone if Armstrong and Aldrin could not launch from the surface. His was the loneliest job in human history, and he accepted it with grace and humor, knowing his role was essential even if it would never be celebrated. The rocket ignited at 1:32 UTC. The first stage, called the SIC, contained 5 F-1 engines, each producing 1.5 million pounds of thrust. Together they consumed 15 tons of fuel per second, burning a mixture of liquid oxygen and kerosene called RP-1. The noise was beyond description, a roar that could be felt in the chest of spectators miles away, a deep subsonic vibration that shook the Earth itself. The rocket climbed slowly at first, fighting gravity with sheer power, rising on a pillar of flame and smoke that stretched behind it like a glowing scar across the sky. The astronauts felt the acceleration build, 2 gs of force pressing them into their seats, then 2.5 gs as the rocket burned fuel and became lighter. The vibration was intense but not unexpected. They had trained in simulators that shook and rattled, but the real thing was always different, always more visceral, always carried the unspoken knowledge that there was no ejection seat, no abort option during the first minute of flight. If something went wrong during that first minute, they would die. But nothing went wrong. The rocket flew perfectly, a testament to the engineers who had designed it, the technicians who had assembled it, the controllers who monitored every sensor and gauge. At 2 minutes and 42 seconds into the flight, the SIC stage burned out and separated, falling away toward the Atlantic Ocean. The second stage, the SI, ignited immediately, 5 J2 engines burning liquid hydrogen and liquid oxygen, a cleaner, more efficient fuel that produced a nearly invisible flame. The ride smoothed out as the second stage pushed them higher and faster. They were above most of the atmosphere now, beyond the buffeting winds and the thick air that had rattled them during the first stage burn. The acceleration continued, building from 2GS to 4GS, pressing them deeper into their seats, making it hard to move their arms, making every breath an effort. At 9 minutes and 8 seconds, the second stage shut down and separated. The third stage, the SIVB, ignited for a brief burn that placed them in Earth orbit. They were moving at 17,500 miles per hour, circling the planet once every 90 minutes, weightless for the first time since launch. They had 2 hours in orbit to check systems, to make sure everything was working correctly, before committing to the journey to the Moon. Mission Control watched the telemetry closely. Every system was nominal. The spacecraft was healthy. The crew was ready. At 2 hours and 44 minutes into the flight, capsule communicator Ron Evans made the call they had been waiting for. Apollo 11, Houston. You are go for TLI. Trans-lunar injection. The burn that would accelerate them out of Earth orbit and send them toward the Moon. Armstrong acknowledged with a simple Roger. The SIVB reignited, burning for 5 minutes and 48 seconds, adding nearly 7,000 miles per hour to their velocity. The acceleration was gentle compared to the launch, only about a half G, but it was sustained, pushing them up through the invisible threshold called escape velocity, the speed at which Earth's gravity could no longer hold them. They were leaving home, crossing the gulf between worlds, beginning a voyage that would carry them farther from Earth than any humans had ever traveled. When the burn ended, they were coasting at 24,300 miles per hour. Ahead of them, the Moon was a distant silver disk, moving through space at its own velocity, and the flight plan called for them to intercept it 3 days hence, arriving at precisely the right point in precisely the right orbit to allow the descent to the surface. Now came the transposition and docking maneuver, one of the most delicate and dangerous parts of the early flight. Michael Collins separated the command module Columbia from the spent SIVB stage, turned the spacecraft around 180 degrees, and flew back toward the lunar module Eagle, which was still attached to the top of the SIVB. He had to dock with Eagle, lock the two spacecraft together, and then pull Eagle free. The maneuver required precision flying in 3 dimensions with no room for error. If he came in too fast, he could damage both spacecraft. If he came in at the wrong angle, the docking probe would not seat correctly and they would not be able to pressurize the tunnel between the vehicles. Collins performed the maneuver perfectly, guiding Columbia toward Eagle with gentle thruster pulses, aligning the docking probe, making contact with a soft metallic click that both he and Armstrong heard through the metal structure of the spacecraft. The probe latched. The docking mechanism pulled the two spacecraft together and locked them. They were now a single vehicle, command module, service module, and lunar module, flying in formation through the void. Collins fired the thrusters again, pulling Eagle free from the SIVB. The spent rocket stage drifted away, and Mission Control sent a command that would fire its remaining fuel in a burn that would send it into solar orbit, out of the way, no longer a hazard. And now the long coast began. 3 days of flying through space, watching Earth recede behind them, watching the Moon grow larger ahead. They were traveling through what is called a free return trajectory, a carefully calculated path that would loop around the moon and bring them back to Earth even if they did not fire their engine again. It was a safety margin, a way to ensure that if something went catastrophically wrong, they would not be stranded in deep space. Gravity would bring them home. But free return trajectories do not pass over the planned landing site. To reach the Sea of Tranquility, they would need to fire the engine and enter lunar orbit, committing themselves to the mission, abandoning the safety of free return. That decision would come later, after 3 days of watching the moon grow from a disk to a sphere to a world. The spacecraft spun slowly as it flew, a maneuver called passive thermal control, or more colloquially, the barbecue roll. Without spinning, one side of the spacecraft would bake in the unfiltered sunlight while the other side froze in shadow. By rolling slowly, the temperature remained relatively even, preventing thermal stress from warping the structure or damaging systems. Inside, the astronauts floated in the strange, silent realm of weightlessness. They ate freeze-dried food rehydrated with water from the fuel cells. They drank orange juice and coffee. They slept in shifts, tethered to their couches with straps to keep from drifting and bumping into equipment. They performed housekeeping tasks, checking systems, adjusting the spacecraft's attitude with gentle thruster burns, reading gauges, calling down status reports to mission control. They also took time to look out the windows. Earth was a beautiful, fragile sphere, 3/4 covered by swirling white clouds, the blue oceans visible beneath, the brown continents of Africa and South America drifting past. The planet seemed impossibly small, hanging in the black void, and the astronauts found themselves thinking about the 6 billion people down there, all living their lives unaware that 3 men were watching from 250,000 miles away. The moon grew larger each hour. At first it was just a bright circle, but soon they could see features, the dark plains of the Maria, the bright highlands, the shadows of crater walls. The moon does not change, not on human timescales. The same craters they were seeing had been there for billions of years, untouched by wind or water or life. It was a dead world, but it was beautiful in its starkness, in the sharpness of its shadows, in the way sunlight reflected off the ancient rock. On July 19, at 75 hours and 49 minutes into the mission, they reached the moon. They were on the far side, out of radio contact with Earth, when the moment came to fire the service propulsion system engine and enter lunar orbit. This was called the Lunar Orbit Insertion Burn, or LOI, and it was one of the most critical moments of the mission. If the engine did not fire, they would loop around the moon and return to Earth, the mission a failure but the crew alive. If the engine fired but did not shut down correctly, they could crash into the moon or be flung into a useless orbit. If the engine fired perfectly, they would enter a 60 by 190 mile orbit that would allow them to descend to the surface. Mission control could do nothing. The spacecraft was behind the moon, blocked by 2,000 miles of rock. No radio signal could reach them. The astronauts were alone, and they would remain alone for 30 minutes until they emerged from the far side. In that time, they would either succeed or fail, and mission control would not know which until they regained contact. Armstrong flipped the switches to arm the engine. The computer counted down. At the exact planned moment, the engine ignited. The astronauts felt the acceleration, a gentle push of about 1 g, far less than the violence of launch but enough to press them firmly into their seats. They watched the clock. The burn was supposed to last 6 minutes and 2 seconds. If it shut down early, they would be in the wrong orbit. If it burned too long, they would crash. The engine burned exactly as planned. 6 minutes and 2 seconds later, it shut down. They were in lunar orbit. They had done it. Now they simply had to wait until they emerged from the far side to tell mission control. When they came around the moon and re-established radio contact, Armstrong's voice crackled through. "Houston, Apollo 11. We're in lunar orbit." The relief in mission control was palpable. Flight Director Gene Kranz allowed himself a brief smile. They were on schedule. Everything was working. The landing was still possible. For the next day, Armstrong and Aldrin prepared for the descent while Collins piloted Columbia. They circled the Moon 30 times, passing over the Sea of Tranquility again and again, photographing the landing site, studying the terrain, looking for obstacles. The site was relatively smooth, but there were craters, boulders, slopes. Landing would not be easy. On the 13th orbit, Armstrong and Aldrin opened the hatch between Columbia and Eagle and floated into the lunar module for the first time since leaving Earth. The lunar module was cramped, Spartan, with no seats and barely enough room for two men in spacesuits. It was not designed for comfort. It was designed to land on the Moon and launch back to orbit, nothing more. They powered up the systems, checking every switch, every circuit breaker, every gauge. The lunar module's computer, another Apollo guidance computer identical to the one in Columbia, came online and began running self-tests. The radar systems powered up. The communication systems checked in. The environmental control system started circulating oxygen. Everything was nominal. Collins inspected Eagle from outside, visually checking the exterior, making sure the landing gear had deployed correctly, looking for any damage that might have occurred during the flight. He saw nothing wrong. The spacecraft was ready. At Revolution 14, Armstrong and Aldrin closed the hatch between Eagle and Columbia. Michael Collins flipped the switches that would separate the two spacecraft. There was a muffled thump as the docking latches released. Collins fired Columbia's thrusters, moving slowly away from Eagle, opening a gap between the vehicles. He flew Columbia to a position above and ahead of Eagle, ready to maintain the orbital formation until the descent began. Armstrong used Eagle's thrusters to rotate the spacecraft slowly, performing what pilots call a pirouette so Collins could visually inspect every surface, every landing leg, every antenna. Collins watched through Columbia's windows, looking for anything amiss, any sign of damage or malfunction. He saw nothing. Eagle looked perfect. The two spacecraft flew in formation for one more orbit. Collins was alone now in Columbia, a single man in a spacecraft designed for three. Armstrong and Aldrin were alone in Eagle, two men standing in a vehicle that had never been flown to a landing before, that had been tested in simulators but never in the real lunar environment. Both crews were ready. Then, at 101 hours, 36 minutes, and 14 seconds into the mission, Houston made the call. "Eagle, Houston. You are go for powered descent." Armstrong acknowledged. Aldrin checked the computer one last time. The descent engine was armed. The landing radar was active. The guidance system showed green lights. They were ready to fall toward the Moon. This is where our story truly begins. Before we can understand the transcript, before we can truly appreciate what Armstrong and Aldrin accomplished during those 13 minutes, we must understand the machine that carried them to the surface. The lunar module was unlike any spacecraft ever built, unlike any vehicle that had come before or would come after. It was purpose-designed for a single, specific task: to land two astronauts on the Moon and launch them back to orbit. Nothing more, nothing less. Every system, every component, every line of code in its computer was optimized for that one mission. The lunar module had no streamlined shape because it would never fly through an atmosphere. There was no need for aerodynamic fairings or smooth curves. It could be angular, awkward, spindly, because in the vacuum of space and on the airless Moon, shape did not matter. What mattered was mass. Every pound of structure was a pound that could not be fuel or equipment. Engineers stripped away everything unnecessary, creating a vehicle that looked like a spider made of gold foil and aluminum struts. It had no seats. The astronauts would stand during the entire descent and landing, held in place by cables and Velcro on the floor. Standing reduced the height of the cabin, which reduced the mass of the vehicle. Standing also gave them a better view out the triangular windows, allowing them to see the surface more clearly during the critical final moments. It was uncomfortable, certainly, but comfort was a luxury they could not afford. The lunar module consisted of 2 stages, stacked one atop the other. The descent stage was the lower half, a squat octagonal platform that housed the descent engine, the fuel tanks, the landing gear, and storage compartments for scientific equipment and moon rocks. It weighed approximately 22,000 pounds fully loaded, most of that weight being propellant. The descent engine was a masterpiece of engineering, the first throttleable rocket engine ever flown in space. It could vary its thrust from 10% to 60%, and then up to 92% for the final descent. This variable thrust capability was essential because the spacecraft's weight decreased continuously as fuel burned, and maintaining the correct deceleration profile required constant adjustment. The descent engine used hypergolic propellants, Aerozine 50 as fuel and nitrogen tetroxide as oxidizer. Hypergolic means the 2 chemicals ignite spontaneously when they come into contact, no spark or ignition system required. This made the engine extremely reliable, because there was no possibility of a failed ignition. But it also made the propellants incredibly toxic and corrosive. Ground crews handling the fuels wore full protective suits, and even a small leak could be catastrophic. Yet in space, these dangerous chemicals were the safest choice, because reliability mattered more than safety margins on Earth. The ascent stage was the upper half, the pressurized cabin where the astronauts stood, surrounded by controls, switches, circuit breakers, and the 2 triangular windows that would give them their view of the moon. The ascent stage also contained the ascent engine, a simpler, fixed-thrust rocket that would fire once to lift them off the surface and into orbit. The ascent engine had no backup, no redundancy. If it failed to fire, Armstrong and Aldrin would be stranded on the moon with no possibility of rescue. It was the single point of failure that kept everyone awake at night, engineers and astronauts alike. But the engine had been tested exhaustively, and it had never failed. That had to be enough. The ascent stage weighed approximately 10,000 pounds fully loaded. When it came time to launch from the moon, explosive bolts would sever the connection between the 2 stages, and the ascent engine would fire, leaving the descent stage behind as a permanent monument on the lunar surface. But the true marvel of the lunar module was not its structure or its engines. It was the brain, the Apollo Guidance Computer. The Apollo Guidance Computer, universally known as the AGC, was a masterpiece of 1960s engineering, a computer built at a time when most computers filled entire rooms, consumed enormous amounts of power, and were far too delicate to survive the violence of a rocket launch. The AGC was different. It was small, weighing only 70 pounds. It was robust, able to withstand acceleration, vibration, radiation, and temperature extremes. It was reliable, with a failure rate measured in hundreds of thousands of hours of operation. And it was powerful enough to navigate to the moon, control the descent engine, manage the spacecraft orientation, and display real-time information to the crew, all simultaneously. The AGC was built using integrated circuits at a time when integrated circuits were a new, unproven technology. Each circuit was a tiny wafer of silicon containing multiple transistors, resistors, and diodes, all interconnected in complex patterns. The circuits were manufactured by Fairchild Semiconductor, and they were expensive, accounting for a significant portion of the AGC's total cost. But they were also reliable and compact, allowing the computer to achieve performance that would have been impossible with discrete components. The AGC had 2 types of memory. Read-only memory, or ROM, was used for storing the computer's programs. The ROM was constructed using core rope memory, a technology so unusual and labor-intensive that it has never been used since. Core rope memory consisted of tiny magnetic cores threaded with copper wires in specific patterns. Each core represented a single bit of data, and the pattern of wires determined whether that bit was a 1 or a 0. The threading was done by hand, mostly by women working at Raytheon, who would spend hours carefully weaving the wires through the cores under magnification, following diagrams that looked like circuit schematics but were actually memory maps. The process was called core rope because of the weaving, and it was called LOL memory by the engineers, which stood for Little Old Lady Memory, a term that sounds quaint and sexist today but reflected the reality that much of the Apollo program's success depended on the meticulous work of women whose names have been largely forgotten by history. These women wove the memory by hand, one wire at a time, creating read-only memory that could not be altered once manufactured. If there was a bug in the software, it could not be patched. The program had to be correct the first time, or the entire memory module had to be discarded and woven again. The AGC also had random access memory, or RAM, which could be read and written during flight. The RAM was constructed using magnetic core memory, a different technology where each bit was stored as the magnetic polarity of a tiny ferrite ring. By applying current to wires threaded through the rings, the computer could flip the polarity, writing data. By sensing the polarity, it could read data. Core memory was non-volatile, meaning it retained its contents even when power was removed, which was essential for a spacecraft where power interruptions could occur during critical maneuvers. The AGC had 36,864 words of core rope memory and 2,048 words of core memory, where each word was 16 bits. In modern terms, that is roughly 72 kilobytes of ROM and 4 kilobytes of RAM. Your smartphone has millions of times more memory. A simple digital watch has more computing power than the AGC. Yet this computer navigated to the moon. It achieved this through elegant software design. The programs running on the AGC were written in a low-level assembly language by a team at MIT's Instrumentation Laboratory, led by a woman named Margaret Hamilton. Hamilton was one of the first software engineers, literally helping to invent the discipline of software engineering as she wrote code for Apollo. She understood that software had to be reliable, had to be robust, had to handle errors gracefully. She developed techniques for prioritizing tasks, for detecting and recovering from errors, for ensuring that critical functions always ran even if less important tasks had to be delayed. The AGC's operating system was called the Executive, and it was a real-time multitasking system, one of the first of its kind. The Executive divided computer time into 20 millisecond slices and allocated those slices to different programs based on priority. The most critical programs, guidance and navigation, ran first. Less critical programs, like updating the display, ran later. If the computer became overloaded, if there were more tasks than time available, the Executive would trigger a program alarm, postpone lower priority tasks, and continue running the essential functions. This architecture was brilliant, but it was also fragile. If the task load became too high, the computer would spend more time managing tasks than actually executing them, creating a snowball effect where alarms triggered more alarms. The programmers had tested the system extensively, trying to break it, trying to find the limits of its capability. But testing could not anticipate every possible scenario. The real world, as Armstrong and Aldrin would discover, had a way of presenting problems that no simulation could predict. The AGC communicated with the crew through the DSKY, pronounced DISKY, the display and keyboard unit. The DSKY was a simple interface mounted on the instrument panel, with a 7-segment digital display showing 5 digits, a set of status lights, and a keyboard with 19 keys. The display could show numbers, but not letters. The keyboard had buttons labeled with verbs and nouns, a unique interface design that reflected the computer's role as a tool that responded to commands. Verbs were actions: display, monitor, load, start, proceed. Nouns were data items: velocity, altitude, time, angles, engine thrust. To interact with the computer, the crew would enter a 2-digit verb code and a 2-digit noun code. For example, verb 16 noun 36 meant display continuously the velocity data. The computer would then show the velocity in 3 axes, updating the numbers several times per second. If the computer wanted to tell the crew something, it would light the prog lamp and display a program number on the DSKY. The crew could then accept the program, reject it, or query the computer for more information. If there was a problem, a yellow comp ACTY light would flash, indicating the computer was working hard, processing many tasks at once. If something went seriously wrong, alarm codes would appear in the display, 2-digit or 4-digit numbers that indicated specific error conditions. The alarm codes had been documented extensively, but there were dozens of them, far too many for the crew to memorize. They had cue cards attached to the instrument panel, small laminated checklists that listed the most critical alarms and what to do about them. But the cards did not list every alarm, and as Armstrong and Aldrin would soon discover, the cards did not explain what some alarms meant. The AGC had been tested more extensively than any computer in history. Engineers had run thousands of simulations, feeding it bad data, interrupting it mid-calculation, overloading it with tasks, trying to find every possible failure mode. They had trained the flight controllers to recognize problems, to diagnose issues, to make go or no-go decisions in seconds. They had created worst-case scenarios and practiced responses until the responses became automatic. But despite all that testing, despite all that preparation, the descent to the moon would reveal a bug that no one had anticipated, a software flaw that would trigger alarms at the worst possible moment, forcing split-second decisions that would determine whether the mission succeeded or failed. For now, though, the computer was ready. The software was loaded. The systems were nominal. And Armstrong and Aldrin were about to trust this 70-pound box of wires and silicon and hand-woven memory to land them safely on another world. The powered descent was divided into 3 phases, each with its own challenges, its own risks, its own beauty. Each phase was controlled by a different computer program, a different set of guidance equations that would steer the spacecraft along a carefully calculated trajectory. These programs had been written months before, tested in simulators, refined through hundreds of practice runs. But this was the first time they would be used for real, the first time the equations would guide a manned spacecraft to a landing on another world. Program 63, known as P63, would handle the braking phase. This was the longest phase, lasting approximately 7.5 minutes, during which the descent engine would fire at maximum thrust to kill the spacecraft's horizontal velocity. Eagle was moving at nearly 3,700 miles per hour when the burn began, skimming over the lunar surface at an altitude of 50,000 feet. P-63's job was to slow that velocity to near zero, transforming orbital motion into a controlled fall, positioning the spacecraft for the final approach. Program 64, or P-64, would guide them through the approach phase, adjusting their trajectory toward the selected landing site. During this phase, the computer would pitch the spacecraft forward, allowing the crew to see the landing site through their windows for the first time. This was when Armstrong would be able to evaluate the terrain, to decide whether the computer's chosen site was safe or whether he needed to take manual control. Program 66, P-66, would manage the final vertical descent to touchdown, a slow, controlled drop from approximately 500 feet to contact with the surface. This was the phase where manual control was expected, where Armstrong would use his judgment and skill to find a safe spot and set the spacecraft down gently. There was also Program 65, which no one wanted to use. P-65 was the abort program, the software that would fire the ascent engine and take them back to orbit if something went catastrophically wrong. P-65 meant failure, meant survival but not victory, meant returning to Earth without landing, without walking on the moon, without achieving the goal that had consumed the nation's attention and resources for 8 years. As Eagle completed its 13th orbit since separation, flying upside down and backwards at an altitude of 50,000 feet above the lunar surface, the moment arrived. Armstrong and Aldrin had completed the checklist, verified every system, aligned the guidance platform, checked the fuel quantity, armed the descent engine. Everything was ready. Everything was nominal. And so the computer began the countdown, a silent digital sequence that would culminate in ignition. The exact moment was 102 hours, 33 minutes, and 5 seconds into the mission measured from the instant of launch 3 days earlier. Ground elapsed time 102:33:05, as Mission Control logged it. Eagle was over the far side of the moon, still out of radio contact with Earth, when the descent engine ignited. Houston could not talk to them. Houston could not help them. For the next several minutes, Armstrong and Aldrin would be completely alone, falling toward the moon with only their computer and their training to guide them. The call came from Mission Control as they emerged from the far side, Houston's voice crackling through the static. "Eagle, Houston. You are go for powered descent." Charlie Duke's voice. Calm, professional, carrying the weight of the go-air no-go decision made by every controller in the room, every engineer in the back room, every person who had worked for years to make this moment possible. They were go. They had permission to attempt the impossible. Armstrong's reply was characteristically brief: "Roger." One word. No elaboration, no emotion. Just acknowledgement that the message had been received and understood. That was Armstrong's style, economy of language, letting action speak louder than words. At 102:33:04.6 ground elapsed time, exactly as planned, the descent engine ignited. The computer had commanded 10% thrust initially, a conservative start to confirm the engine was working, to make sure the combustion was stable, to give the crew a chance to abort if something went wrong. 10% thrust was 987 pounds of force, barely enough to notice in the spacecraft, just a gentle push against their feet as they stood at the control panels. 5 seconds later, satisfied that the engine was firing correctly, the computer commanded full thrust. The descent engine roared to life, if roar is the right word for something burning in silence, in vacuum, where no sound can propagate. The astronauts felt it, though. They felt the deck press upward against their boots. They felt the vibration through the metal structure. They felt the spacecraft begin to slow, to change its trajectory, to fall. 9,870 pounds of thrust. Pushing against the spacecraft's forward motion, against its orbital velocity, against the pull of lunar gravity. The physics were simple but unforgiving. They were moving too fast to fall straight down. They had to shed that horizontal velocity first, transforming their trajectory from a shallow ellipse into a steep, controlled descent. The engine would burn continuously for the next 12 minutes and 17 seconds, consuming propellant at a rate of nearly 90 pounds per second, gradually emptying the fuel tanks as the spacecraft grew lighter and lighter. Eagle began to slow down, dropping out of orbit. The computer-controlled descent had begun. For the next 12 minutes, everything would depend on the interplay between human judgment and machine precision, on the trust between crew and controllers, on the reliability of systems built by thousands of engineers who would never fly to the moon themselves but whose work would determine whether these two men lived or died. Armstrong spoke, his voice calm, "Got the Earth right out our front window." He was describing what he saw, providing situational awareness to Mission Control, letting them know that the spacecraft's orientation was correct. The Earth, the distant blue and white sphere, hung in the black sky above them, visible through Eagle's triangular windows. It was a reminder of how far they had come, a reminder of the millions of people watching and waiting, a reminder that home was very far away and getting farther with every second. Houston replied, a simple acknowledgement, "Roger, Eagle." In mission control, the tension was rising. The flight controllers sat at their consoles, eyes locked on their displays, watching the telemetry stream in from Eagle. They could see the descent engine firing. They could see the velocity decreasing. They could see the altitude starting to drop. Every number was nominal, but nominal only meant that nothing had failed yet. The descent was just beginning, and there were 1,000 ways it could still go wrong. Gene Kranz, the flight director, stood at the center of the room, monitoring his team, ready to coordinate responses to any problem that might arise. He wore his trademark white vest, a lucky charm that his wife had sewn for him, the same vest he had worn during Gemini missions, during earlier Apollo missions. White for a lunar landing, white for history, white because Kranz believed that leaders should be visible, should stand out, should be unmistakable in a moment of crisis. Around him, the controllers worked their consoles. Steve Bales, the guidance officer, monitored the AGC's performance, watching the computer's calculations, ready to call abort if the guidance system failed. Bob Carlton, the flight dynamics officer, tracked the trajectory, comparing the actual descent path to the planned path, checking for deviations. Jay Green, the flight dynamics officer, watched the fuel consumption, calculating how much time they had left, how much margin remained. Each controller had abort authority. Any one of them could call for Eagle to abort the landing if they saw something wrong, and that call would be final, immediate, no appeals, no second guessing. But for now, everything was nominal. The engine burned. The altitude decreased. The numbers on the DSKY changed rapidly as the computer calculated their position, velocity, and remaining fuel 1,000 times per second, updating the guidance equations, adjusting the engine thrust, steering them toward the landing site with mathematical precision. Aldrin called out the numbers from the DSKY, his voice steady, reading the data that Armstrong needed to monitor their progress, going right down the line. Delta H is minus 3,640 feet per second. Delta H, or delta height, was the rate of change in altitude. It was a velocity, measured in feet per second, and the negative sign meant they were descending. 3,640 feet per second. That was their vertical velocity at that moment, a number that would decrease throughout the burn as they slowed down. By the time they reached the surface, Delta H would be close to zero, just a gentle descent rate of a few feet per second, slow enough to land without damaging the spacecraft. At 1:02:34:40, about 90 seconds into the burn, Houston called up a routine check. Eagle, Houston. Altitude velocity light. They were asking about a specific indicator on the DSKY, a light that would illuminate when the landing radar began tracking the surface. The radar was essential. The computer's inertial navigation system, which measured acceleration and integrated it to calculate position and velocity, was accurate enough to fly through space, to navigate between Earth and Moon, to manage orbital maneuvers. But it was not precise enough for landing. Small errors in acceleration measurement would accumulate over time, creating position errors that grew larger the longer the system operated. By the time they reached the surface, those errors could be hundreds of feet, far too large to ensure a safe landing. The landing radar solved this problem by measuring actual altitude and velocity relative to the Moon's surface. It transmitted radio beams downward at 4 different angles, and by measuring the time it took for each beam to reflect back, it could determine both altitude and velocity with precision. The radar data would feed into the guidance equations, correcting the inertial navigation errors, refining the descent trajectory, ensuring they landed where the computer intended. Armstrong acknowledged the call, "Roger." Altitude velocity light. The light was on. The radar was working. The computer was receiving good data. This was a critical milestone, a confirmation that one of the most important systems was functioning correctly. Without the radar, the landing would have been far more dangerous, would have required manual navigation, would have depended entirely on Armstrong's ability to judge altitude and descent rate by eye. With the radar, the computer could handle the navigation, leaving Armstrong free to focus on finding a safe landing site. Armstrong spoke again, a brief observation: throttle down better than the simulator. The engine had throttled down from full thrust to a programmed intermediate level, and the transition had been smoother than it had been during the simulations they had run on Earth. These small confirmations mattered immensely. They suggested the hardware was performing as designed, that the real world matched the thousands of practice runs they had flown in the simulator. Every time something worked as expected, it increased their confidence, reduced their stress, allowed them to focus on the things that might not go as planned. The spacecraft was now deep into the braking phase, using maximum thrust to kill horizontal velocity while maintaining some vertical descent. The goal was not to hover, which would waste precious fuel, but to follow a carefully calculated trajectory that would bring them to a point 12,000 feet above the surface, from which the final approach could begin. The trajectory was a compromise between fuel efficiency and safety, between going fast enough to minimize burn time and going slow enough to maintain control. Aldrin continued calling out the numbers, his voice steady and mechanical, reading from the DSKY with the precision of a metronome. 6 + 2 5, throttles down to about 56. He was reading multiple pieces of information simultaneously. The descent engine was running at 56% thrust. 6 + 2 5 was a time or position readout, part of the stream of data the computer displayed. Every number meant something specific, and both astronauts had memorized what each one represented. They had spent hundreds of hours in the simulator, practicing these callouts, learning to interpret the numbers instantly, training themselves to spot anomalies before they became emergencies. The descent continued. Altitude decreasing. Velocity slowing. Fuel burning. The computer flying them toward a point on the surface that had been chosen months earlier by scientists and engineers who had studied photographs taken by earlier lunar missions, who had analyzed the terrain for slopes and boulders, who had selected the Sea of Tranquility as the safest place to land. But photographs from orbit do not show everything. They do not reveal the small craters, the scattered rocks, the subtle slopes that could tip a spacecraft or damage a landing leg. Those details would only become visible during the final minutes of the descent, when Armstrong could see the surface directly and make the decision to trust the computer or to take control and fly somewhere else. For now, though, he let the computer fly. The descent was proceeding nominally. The numbers were good. The engine was performing beautifully. Everything was working. And then, at 1:02:38:58, as Eagle passed through 33,000 feet, something unexpected happened. At 1:02:38:58, as Eagle passed through 33,000 feet, something unexpected happened. Aldrin, program alarm. His voice remained calm, but those two words sent a jolt through mission control. Program alarms meant the computer had detected a problem. Armstrong, it's a 12:02. The DSKY displayed 12:02. Neither Armstrong nor Aldrin knew exactly what that meant. They had been trained on alarm codes, but there were dozens of them, and no human could remember every one under stress. They looked at their cue cards, small checklists attached to the instrument panel, but the cards did not explain what 12:02 meant. They only listed a few critical alarms and what to do about them. Aldrin, 12:02. He was confirming it to Houston. In mission control, Charlie Duke immediately queried his back room, the separate room where engineers monitored telemetry and supported the flight controllers. Duke, we got you. We go on that alarm. The response came in seconds, but those seconds felt eternal. Steve Bales, the guidance officer, had seen the alarm code in his data. He quickly called Jack Garman, a computer engineer in the back room who had studied alarm codes extensively. Garman knew instantly what 1202 meant: executive overflow. The computer was being asked to do too many things at once. It was detecting that it could not complete all its tasks in the time available, so it was postponing lower priority jobs and resetting itself to prevent a crash. The critical tasks, guidance and control, were still running. The alarm was essentially the computer saying, "I'm busy, but I'm handling it." Garman told Bales, "We go on that alarm." Bales told the flight director. Kranz made the call to continue. Duke relayed it to the crew. But why was the computer overloaded? It would later be determined that the rendezvous radar, which Eagle would need to find Columbia after liftoff from the Moon, was left in the wrong mode. It was sending data to the computer even though the computer did not need it yet. The unnecessary data was stealing processing time from the guidance equations, creating the overflow. The radar had been left in that mode deliberately. The astronauts wanted it ready in case they had to abort the landing and return to Columbia immediately. But no one had fully understood how much the extra data would burden the computer during the descent. It was an oversight, a gap in testing, the kind of thing that simulations cannot always reveal. For now, though, the alarm cleared. The descent continued. Armstrong, give us a reading on the 1202 program alarm. He wanted confirmation they could keep going. He was asking Mission Control to double-check, to make sure this was not a critical failure. Duke, Roger. We got you. We go on that alarm. Armstrong said nothing more. He did not need to. Houston had said go. That was enough. But the relief was brief. Aldrin continued calling out data from the DSKY. The stream of numbers was constant, a rhythmic cadence that kept both astronauts and Mission Control informed of the descent's progress. Aldrin, AGS and PGNS are virtually identical. The AGS was the abort guidance system, a completely separate computer installed as a backup. It had its own sensors and its own calculations. If the AGC failed completely, the AGS could take over and fly the lunar module back to orbit. Aldrin was confirming that both computers agreed on their position and velocity, which meant the data was trustworthy. Duke, Roger. Aldrin, 12,000 feet. They were now at 12,000 feet above the surface, approaching the transition from the braking phase to the approach phase. The computer would soon pitch the spacecraft forward, allowing the crew to see the landing site through their windows for the first time. Aldrin, 9,000 feet. The altitude was dropping steadily. The descent engine was still throttled back, maintaining the programmed trajectory. Everything was going according to plan, but everyone knew the plan was only as good as the next second. At 1:02:40:30, the alarm returned. Aldrin, 12:01. Another alarm. Not quite the same as before, but close. Same root cause, executive overflow. The computer was still being overloaded by the rendezvous radar data. Armstrong, 12:01. His voice was still calm, but the repetition of alarms was unsettling. The crew needed to focus on flying the spacecraft, not on troubleshooting the computer. Duke, Roger. 12:01 alarm. In Mission Control, Bales and Garman conferred again. The 12:01 alarm was similar to the 12:02, the computer detecting it was too busy, postponing non-critical tasks, continuing with guidance and control. They were go. Duke, we're go. Same type. We're go. Armstrong acknowledged with a brief "Roger." The alarms would recur several more times during the descent, always the same codes, always the same cause. Each time, Mission Control would quickly confirm they were go. But the alarms were eating into the crew's mental bandwidth, forcing them to divide their attention between flying and worrying about the computer. In the years after Apollo 11, the alarm issue would be studied exhaustively. Software would be rewritten. Procedures would be changed. But on July 20, 1969, Armstrong and Aldrin simply had to trust that Houston knew what they were talking about, and that the computer would keep working despite its complaints. At 12,000 feet, the computer executed Program 64. Eagle pitched forward, rotating from its previous attitude so the astronauts could see the lunar surface through the windows. For the first time since starting the descent, they had a visual reference. Aldrin got the shadow out there. The shadow of the lunar module on the surface below, a small dark shape against the gray dust. It gave them a sense of height and motion. The shadow seemed to race across the craters and rocks, even though Eagle was still several thousand feet above the ground. Armstrong was now watching the surface intently. The computer was steering them toward a landing site designated by a simple coordinate, but Armstrong could see that the actual terrain did not match what they had expected. There were boulders. Large ones. And a crater, much bigger than anticipated, right in the path the computer was taking them. He said nothing yet. He was still letting the computer fly, but his hand rested on the attitude controller, ready to take over if needed. The plan called for the computer to bring them to 500 feet, at which point Armstrong would take manual control for the final touchdown. But if the computer was flying them into danger, he could take over earlier. Aldrin, 7,000 feet. Duke, Eagle, Houston. You'll go for landing. This was a critical call. Houston was confirming they had enough fuel, enough time, and acceptable systems to attempt the touchdown. If anything had looked wrong, Houston would have called for an abort. But everything checked out. They were go. Armstrong, Roger. Understand. Go for landing. 3,000 feet. The altitude was dropping fast now. 3,000 feet. Then 2,000. Aldrin was reading off the numbers rapidly, calling out altitude and descent rate in a steady rhythm that kept Armstrong informed without requiring him to look at the DSKY. Aldrin, altitude velocity light. 35 degrees. 35 degrees. 750 feet. Coming down at 23. 700 feet. 21 down. 33 degrees. 600 feet. Down at 19. The pattern of his callouts was precise. Altitude first, then descent rate in feet per second, then pitch angle. Each piece of information told Armstrong whether they were following the planned trajectory. But Armstrong was not looking at numbers now. He was looking at the boulders. The computer was guiding them toward the east side of a crater filled with rocks the size of cars. Landing there would tip the lunar module over, damaging the ascent stage and stranding them on the moon. At 102:42:40, Armstrong made the decision. He took over manual control. The lunar module had two modes of manual control. Mode 3, called semi-automatic, allowed Armstrong to fly the spacecraft horizontally while the computer maintained vertical descent rate. Mode 1, full manual, gave him complete control. Armstrong selected Mode 3. He moved the hand controller to the right, steering Eagle away from the boulder field. The computer would still manage the descent rate and keep them upright, but Armstrong would choose where they landed. Aldrin, 540 feet. Down at 15. Altitude velocity light. The AV light was on again, confirming the radar data was good. But the altitude was getting low. Very low. Aldrin, 400 feet. Down at 9. Armstrong was flying now, not just monitoring. He was scanning the surface, looking for a smooth area. Every second of flight consumed fuel they would never get back. The fuel gauge was dropping. Aldrin, forward. Forward. Good. 40 feet. Down 2.5. Picking up some dust. The descent engine's exhaust was beginning to stir up lunar dust. The dust, with no atmosphere to slow it down, flew outward in perfectly straight lines, creating a strange, crystalline pattern. It obscured the surface, making it harder for Armstrong to judge the terrain. Aldrin, 30 feet. 2.5 down. Faint shadow. They were so low now that the lunar module's shadow was visible in the dust. Armstrong was still moving forward, still searching. Duke, 60 seconds. That call from Houston was terse, almost harsh. 60 seconds. 60 seconds of fuel remaining. In 60 seconds, they had to be on the ground, or they had to abort. There was no third option. Armstrong did not reply. He was entirely focused on flying. Aldrin, forward. Forward. Good. 40 feet. Down 2.5. Picking up some dust. 30 feet. 2.5 down. Faint shadow. For forward. For forward. Drifting to the right a little. The callouts were coming faster now, almost urgent. Aldrin was giving Armstrong every piece of information he could, helping him understand the spacecraft's motion without looking away from the surface. Inside Mission Control, the tension was unbearable. The flight controllers watched their screens, seeing the fuel quantity dropping, watching the altitude decrease. Bob Carlton, the retro officer, had his hand on the button that would initiate an abort. He was waiting for the flight director's call. Gene Kran stood at his console, listening to the data, watching his team. He knew they were seconds from landing or aborting, and he could not help. The crew was too low, too close. If they aborted now, the ascent stage engine would fire, blowing them back into orbit, but the flames would likely damage the descent stage still beneath them. It would be a violent, dangerous ascent with no guarantee of success. But landing with no fuel was not an option either. Duke, 30 seconds. 30 seconds. Aldrin heard it. Armstrong heard it. But Armstrong did not abort. He kept flying. He had found a spot. A clear area beyond the boulder field. He was nearly there. Aldrin, contact light. Okay, engine stop. A blue light on the panel. Contact light. One of the 68-inch probes hanging from Eagle's footpads had touched the surface. The instant Armstrong saw it, he shut down the engine. The spacecraft dropped the final few feet and settled onto the moon. There was a metallic crunch as the landing gear compressed. The astronauts felt a slight jolt. Then stillness. Armstrong, shut down. Aldrin, okay, engine stop. ACA out of detent. He was reading from the checklist, shutting down systems in the correct sequence. Aldrin, mode controls, both auto. Descent engine command override, off. Engine arm, off. 413 is in. 413 was a code on the abort guidance system indicating they had landed. Aldrin was confirming every step, following procedures, making sure nothing was forgotten. Armstrong, we copy you down, Eagle. No. Wait. That was the call he expected to hear from Houston. But Houston was silent. Everyone was holding their breath, waiting. Armstrong keyed his microphone. His voice was steady, almost casual, as if he had just parked a car. Armstrong, Houston, Tranquility Base here. The Eagle has landed. Tranquility Base. Not Eagle anymore. They were no longer a spacecraft. They were a base. A human outpost on another world. There was a pause. A brief, stunned silence from Mission Control. Then Charlie Duke's voice came through, and for once, the professional astronaut's composure cracked. His words tumbled out in a rush, relief and joy overwhelming training. Duke, Roger, Twan, Tranquility, we copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. Scattered applause broke out in Mission Control. Controllers grinned at each other, shook hands, lit cigars. Gene Kranz allowed himself a slight smile. Armstrong, thank you. Aldrin, okay, let's get on with it. Okay, we're going to be busy for a minute. Because there was still work to do. Landing was not the end. It was the beginning. They needed to verify all systems were stable, that nothing had been damaged, that they could safely stay on the surface. And they needed to determine if they could launch again when the time came. But for now, for this one perfect moment, they had done it. They had landed on the moon. When the dust settled, quite literally, the analysis began. How much fuel had been left? The official figure was 216 pounds of usable fuel remaining. At the descent engine's throttle setting during the final seconds, that represented approximately 45 to 50 seconds of hover time, not the 25 seconds suggested by the 60-second call-out. The discrepancy came from how fuel was measured. The gauges measured quantity based on pressure and temperature, and those readings were conservative. There was actually more fuel available than the instruments indicated, a safety margin built into the system. But even 50 seconds was a razor-thin margin. If Armstrong had not found a landing spot when he did, if he had needed to fly another 100 feet, he would have been forced to abort. The landing site was not where it was supposed to be. The computer had been aiming for a point in the Sea of Tranquility, but trajectory errors during the descent, tiny inaccuracies in the initial orbit, and the effects of the moon's uneven gravity field had carried them downrange. They landed for miles beyond the intended target, at coordinates 0 degrees, 40 minutes, 26.69 seconds north latitude, and 23 degrees, 28 minutes, 22.69 seconds east longitude. Armstrong's manual flying had added to the deviation. He had flown Eagle horizontally for nearly a minute, covering an additional distance as he searched for a safe spot. But that decision had saved the mission. The computer's target site was indeed filled with boulders and craters that would have destroyed the spacecraft. Years later, in interviews and debriefings, Armstrong would describe the landing as the most challenging part of the entire mission. The powered descent on Apollo 10 had gone smoothly, but that was a rehearsal. Apollo 11 was the real thing, with real consequences. He said the unknowns were rampant, the terrain uncertain, and the decisions required came so quickly there was no time for doubt. But he never expressed drama or fear when he spoke of it. He spoke in the language of engineering, problems, solutions, margins. That was how he had been trained to think, and it had served him well. It is worth pausing here to consider what was actually happening in those 13 minutes. Two human beings, sealed inside a fragile metal shell, were falling toward an airless world at thousands of miles per hour. They were trusting a computer no more powerful than a pocket calculator to execute equations that would determine whether they lived or died. Every number on the DSKY, every alarm, every call-out was a lifeline. The transcript we have been reading is not a story. It is not a narrative crafted for drama. It is simply the record of what was said. But within that dry recitation of altitudes and velocities lies something profound: trust. Armstrong and Aldrin trusted the engineers who designed the systems. They trusted the flight controllers who analyzed the data. They trusted each other. And most of all, they trusted the procedures, the checklists, the training. They had rehearsed this descent hundreds of times in simulators. They knew what every number meant, what every alarm indicated, what every switch did. But they also knew that no simulation was perfect. The moon was real. The boulders were real. The fuel running low was real. And so when Armstrong took control and flew manually, he was not abandoning the plan. He was adapting it. He was doing what human beings do best: improvise when the world does not match expectations. Aldrin's role was equally critical. He read the instruments, called out the numbers, managed systems, kept Armstrong informed without distracting him. It was a partnership built on years of training and mutual respect. Neither man could have landed alone. And in Houston, the flight controllers were the invisible third crew member. They monitored data the astronauts could not see, made calculations the astronauts did not have time to perform, and provided the go and no-go calls that cleared the way forward. When Steve Bales said go on the 12:02 alarm, he was taking a risk. If he was wrong, 2 men would die. But he trusted his training, trusted Jack Garman's expertise, and made the call. That is what the transcript reveals when you read it carefully. Not just a sequence of events, but a web of trust spanning 250,000 miles. Welcome back to Sleep Orion. In Part 1, we followed Neil Armstrong and Buzz Aldrin through the 13-minute powered descent to the lunar surface, listening to every call-out, every alarm, every tense second as fuel ran low and decisions had to be made in fractions of time. We heard the computer alarms that could have ended the mission, heard Armstrong's calm voice as he took manual control, heard Aldrin's steady stream of numbers guiding them down. We heard the Eagle has landed, and we heard Charlie Duke's breathless reply, the relief spilling through his words as Mission Control collectively exhaled after holding their breath for 13 minutes of controlled terror. Now, in Part 2, we will explore what came after that landing, what those 13 minutes meant both technically and historically, and what the transcript reveals about the intricate dance between humans and machines in the most extreme environment imaginable. We will dig into the technical details, unpack the decisions made in split seconds, examine the systems that worked perfectly and the ones that nearly didn't, and consider how this single event reshaped humanity's understanding of what is possible. The descent transcript is more than just a historical record. It is a window into human achievement at its finest, a document that captures both the poetry and the mathematics of exploration, the interplay of courage and calculation, the trust between people separated by thousands of miles but united in purpose. Settle in once again. Let your mind drift to that July day in 1969, to the moment when the impossible became real, recorded in the simple words and numbers of men doing their jobs under unimaginable pressure. Let's continue. When the Eagle settled on the moon's surface at 1:02 to 45 to 40 ground elapsed time, there was no time for celebration, no moment to savor what they had just accomplished. The work continued immediately, seamlessly, with the same intensity and focus that had carried them through the descent. Within seconds, Armstrong and Aldrin were running through the post-landing checklist, a series of critical steps designed to ensure they could stay on the surface safely, that they had not damaged the spacecraft during touchdown, that all systems remained functional. The primary concern was brutally simple: could they launch again? If the landing had damaged the ascent stage engine, if the lunar module had tipped too far and the engine bell was not pointed straight up, if a fuel line had ruptured, if the landing gear had buckled, if any one of 1,000 systems had failed during the touchdown, they needed to know immediately. Because if they could not launch, if the ascent stage engine would not fire or could not reach orbit, they had perhaps 2 days of life support before the oxygen ran out and they suffocated in their suits, alone on an alien world with Earth hanging in the sky above them, close enough to see but impossibly far away. Mission Control faced the same question from a different angle, from the perspective of telemetry and numbers rather than direct observation. The flight controllers were scanning their displays, checking every sensor reading, every system status indicator, every data point streaming down from Eagle, looking for anything abnormal, anything that suggested damage or malfunction. They had only minutes to make the first critical decision: stay or abort immediately. This was called the one stay, no stay decision, the first planned decision point, the first commitment to remaining on the surface rather than launching back to orbit as quickly as possible. If everything checked out during T1, there would be a T2 decision several minutes later, then a T3, each decision point extending their stay on the Moon, each one representing a deeper commitment to the mission plan. But if anything looked wrong during T1, if any controller saw a problem, they would call for an immediate abort, and the ascent stage engine would fire within minutes, blowing them back into orbit before a small problem could become a fatal one. The transcript resumes, the voices calm but urgent, the professionalism never wavering even as the stakes could not be higher. "Duke, we'd like you to check your RCS quantity, Eagle." The Reaction Control System, RCS, used small hypergolic thrusters mounted around the spacecraft to control attitude, to rotate the vehicle, to make small adjustments to its orientation. The RCS fuel was separate from the descent engine fuel, stored in different tanks, and the quantity of propellant in those tanks needed to be verified immediately. If there had been a leak during descent, if a thruster had fired inadvertently, if a fuel line had been damaged during touchdown, the RCS quantity would be lower than expected, and that would indicate a serious problem. Aldrin responded immediately, "Okay. I'll check it." There was a brief pause, perhaps 5 seconds, as Aldrin scanned the gauges, reading the numbers, comparing them to what they should be. 5 seconds of silence that felt much longer to everyone listening, to Mission Control waiting for the data, to Armstrong standing beside Aldrin in the cramped cabin, both of them aware that their lives might depend on those numbers. Aldrin, "Okay, Houston. I show 65% in each RCS. Duke, Roger. We copy." The reply was laconic, almost casual, but the relief was implicit. 65% was good. The RCS tanks were nominal. No leaks. The system was healthy. That was one critical check complete, one potential failure mode eliminated, one step closer to a stay decision. Next came a qualitative assessment, Armstrong's description of what had happened during the final seconds of the descent, his explanation of why they had landed downrange from the planned target, why he had taken manual control. "Armstrong, we'll get to the details." That may have seemed like a very long final phase. The auto-targeting was taking us right into a football field-sized crater, with a large number of big boulders and rocks, and it required flying manually over the rock field to find a reasonably good area. His voice was calm, measured, describing the manual flying as if it had been a routine maneuver, as if flying a spacecraft horizontally at low altitude with fuel running out was just another day at the office. But the underlying message was clear and critical: the computer would have killed them. The guidance system, despite all its sophistication and testing, had been steering them toward a landing site filled with hazards. He had been forced to take control, to override the computer, to search for a safe spot while fuel drained away and time ran out. That information was vital for Mission Control to understand. It explained the trajectory deviation, the extended powered flight, the fuel consumption that had brought them so close to bingo. It also raised questions for future missions. Why had the computer chosen that site? Was it a targeting error, a guidance problem, or just bad luck that the designated landing area happened to have a crater the orbital photographs had not revealed? Those questions would be analyzed later, studied exhaustively, used to improve procedures for Apollo 12 and beyond. But for now, the immediate concern was simpler: they were on the ground, and they needed to determine if they were safe. Duke, Roger. We copy. It was beautiful from here. Tranquility. Over. Beautiful. An interesting word choice, perhaps the only moment of poetry in the technical exchange. Mission Control could not see what Armstrong saw. They had no television view yet, no camera showing them the boulder field or the crater or the dust blowing across the lunar surface. They could only watch numbers on screens, telemetry data streaming down, graphs and indicators showing altitude, velocity, attitude, fuel quantity. But those numbers told a story, and the story was beautiful because it ended in success, because 2 men were alive on the moon, because the mission had not ended in catastrophe. Armstrong continued his observation, transitioning already from pilot mode into science mode, beginning the work of describing the surface for the engineers and geologists who would study every word. Armstrong, we'll get to the details of what's around here, but it looks like a collection of just about every variety of shape, angularity, granularity, every variety of rock you could find. There doesn't appear to be too much of a general color at all. However, it looks as though some of the rocks and boulders are going to have some interesting colors to them. He was observing, cataloging, describing. The test pilot had become a field geologist, studying an alien landscape, providing data that would guide the moonwalk, that would help the scientists understand what they were seeing when the television camera activated, that would inform decisions about where to walk, where to collect samples, where to set up experiments. But there were still systems to check, still procedures to complete before they could think about opening the hatch and stepping outside. Aldrin began reading off status indicators, working through the post-landing checklist item by item. Aldrin, master arm is off. I've got the mission timer going and I have the event timer reset. And he was interrupted by Mission Control, a request taking priority over the checklist. Duke, Eagle, Houston. We'd like you to go to P00 and accept data. P00 was Program 00, an idle program that essentially told the AGC to stop whatever it was doing and wait for new instructions. The computer would enter a quiescent state, maintaining basic systems but not running any guidance programs, not calculating trajectories, not controlling the spacecraft's attitude. In P00, the computer could receive data uploads from Mission Control, could be reprogrammed remotely, could accept new coordinates, new abort plans, new contingency procedures. Aldrin, Roger. P00 and accept. He punched the commands into the DSKY, verb 37 enter, program 00 enter. The computer acknowledged, the display showing P00, the comp ACTY light flashing briefly as it transitioned between programs. Data began flowing up from Houston, a stream of binary commands transmitted at 2,100 bits per second, updating the computer's memory with new information calculated by the trajectory team on the ground. They were uploading new abort trajectories based on Eagle's actual landing position, not the planned position. If something went wrong during the surface stay, if they needed to launch immediately, the computer would need to know exactly where they were, exactly what trajectory to fly to reach Columbia in orbit. Michael Collins was still up there, circling alone, maintaining the orbital parameters, waiting for his crewmates to return. The computer needed fresh data to find him. Meanwhile, the controllers in Houston were making their assessments, each console running through its checklist, each specialist evaluating their systems, each voice reporting into the flight director. The process was formal, ritualized, a verbal confirmation that each aspect of the mission had been checked and found acceptable. FIDO, go. Guidance, go. Control, go. Telcom, go. Surgeon, go. Capcom, we're stay for T1. Gene Kranz heard each voice, acknowledged each report. Fido, the flight dynamics officer, had checked the trajectory and landing site. Guidance had verified the AGC was healthy. Control had confirmed the attitude control system was functioning. Telcom had good communication links. Surgeon had reviewed the crew's medical telemetry and found them stable. Every system was nominal. Every controller was satisfied. They would go for T1. Duke made the call, his voice carrying the weight of Mission Control's collective judgment. Eagle, Houston. Your stay for T1. Aldrin acknowledged simply, Roger. T1 stay. It was official. They were not launching immediately. They would remain on the surface at least until the next decision point. The mission could continue. The moonwalk was still possible. The dream was still alive. Now that they had confirmed they could stay, Armstrong and Aldrin began shutting down non-essential systems to conserve power and cooling. The lunar module's batteries were not infinite, and the environmental control system could only handle so much heat. Every piece of equipment that remained on generated heat and drained power. Aldrin, okay. We're going to get busy with the post-landing checklist here. The post-landing checklist was dozens of items long, each step designed to configure the spacecraft for surface operations. Some systems needed to stay on. Others could be powered down. The crew moved through the list methodically, flipping switches, reading gauges, confirming that every step was completed correctly. In the background, Mission Control continued analyzing data. They were comparing the actual landing site to the planned site, calculating how much fuel had really been left, checking for any anomalies in the telemetry. One important question was the tilt of the spacecraft. The lunar module's landing gear had been designed to accommodate slopes up to 12 degrees. If the spacecraft was tilted beyond that, the ascent stage engine might not fire correctly, or worse, the exhaust could strike the surface and reflect back into the engine bell, destroying it. Armstrong had reported that the tilt felt minimal, but feelings were not enough. They needed numbers. Duke, Tranquility, Houston. We'd like you to read us your DSKY altitude and velocity readouts. The computer's final altitude and velocity measurements would help Mission Control refine their estimate of the landing site. Aldrin read the numbers from the DSKY. Houston copied them, fed them into trajectory computers back on Earth, and began refining the calculations. Meanwhile, Armstrong was looking out the window, describing the surface. Armstrong, it's quite dark here in the shadow, and a little surprising. I can see some of the area in the shadow, but I can see the rocks out there. The surface appears to be very, very fine-grained, as you get close to it. It's almost like a powder. This was important scientific information. Before Apollo 11, there had been genuine concern that the lunar surface might be covered in deep dust that would swallow the spacecraft. Some scientists had predicted the dust could be meters deep, accumulated over billions of years of micrometeorite impacts. Armstrong's observation confirmed that the surface was solid, that the landing gear had not sunk into fine powder. Aldrin added, it has a stark beauty all its own. It's like much of the high desert of the United States. It's different, but it's very pretty out here. Stark beauty. High desert. These were poetic descriptions from men trained as engineers and pilots. But poetry was perhaps the only language adequate to describe what they were seeing, a place no human eyes had ever witnessed firsthand. As the minutes passed, Mission Control reached the next decision point, T2. This was a longer stay commitment. If they said stay for T2, it meant the crew would remain on the surface long enough to prepare for the moonwalk. The controllers ran through their checklists again. Every system was nominal. Consumables were as expected. The landing site was stable. There was no reason to abort. Duke, Tranquility, Houston. You are stay for T2. Aldrin, Roger. Stay for T2. They were committed now. The moonwalk was going to happen. Armstrong and Aldrin were going to open the hatch, climb down the ladder, and step onto the moon. But that would take hours of preparation. First, they needed to complete the post-landing procedures. Then they needed to eat, rest, and suit up. The moonwalk had been planned for several hours after landing, giving the crew time to verify systems and prepare properly. However, the original flight plan had assumed the crew would sleep first, then perform the moonwalk after resting. But Armstrong and Aldrin requested to move the moonwalk earlier. They were awake, alert, and eager to proceed. Sleeping would be difficult in the cramped, noisy lunar module with adrenaline still coursing through their veins. Better to do the moonwalk now, while they were sharp, and sleep afterward. Mission Control agreed. The timeline was adjusted. The moonwalk would begin in a few hours. One of the most critical post-landing tasks was safing the descent engine. The engine had done its job, bringing them to the surface, but it was now sitting beneath them, its fuel tanks still pressurized, its systems still active. If something went wrong, if a valve leaked or a line ruptured, hypergolic fuel could spray into the spacecraft or ignite, destroying everything. The safing procedure involved venting the remaining fuel, depressurizing the tanks, and isolating the engine from the rest of the spacecraft systems. It was a delicate operation, requiring precise switch sequences and careful monitoring. Aldrin worked through the checklist. Aldrin, descent engine command override, off. Descent engine arm, off. Descent heat valves, closed. Descent oxidizer valves, closed. Each switch movement was deliberate, confirmed by checking indicator lights and gauge readings. A single mistake could have catastrophic consequences. Duke, Roger. We copy. Houston was monitoring the telemetry, watching the same pressures and valve positions that Aldrin was watching. If anything looked wrong, they would call it out immediately. But everything went smoothly. The descent engine was saved. It would never fire again. Its job was done. As the post-landing checklist neared completion, Armstrong and Aldrin began preparing for the moonwalk. This was formally called an extravehicular activity, or EVA. It required both astronauts to don their portable life support systems, or PLSS, the backpacks that would provide oxygen, cooling, and carbon dioxide scrubbing during the 4-hour surface excursion. But first, they had to deal with a more immediate problem. The lunar module's interior was cramped. With both astronauts standing up, there was barely room to move. Adding bulky backpacks made it nearly impossible. The process of getting into the PLSS was a carefully choreographed sequence of movements. One astronaut would help the other into the backpack, then reverse roles. Each step required communication, coordination, and patience. Aldrin, okay, Neil. I'll start to unstow the PLSS. Armstrong, okay. The backpacks had been stored in the aft section of the cabin, secured with straps and clamps. Aldrin released them, careful not to bump any switches or controls. In zero gravity, this would have been easier, but on the moon, the backpacks had weight. Not Earth weight, but enough to make them cumbersome. Armstrong began putting on his backpack first, threading his arms through the straps while Aldrin guided it into place and secured the latches. Armstrong, got it. Aldrin, yeah. Let me check the connections. The PLSS had multiple connectors, oxygen supply, water cooling, electrical communications. Each had to be mated correctly, verified, and tested. A loose connection could mean a failed life support system during the EVA, which would immediately end the moonwalk and possibly endanger the crew. They worked through the checklist methodically, testing each system. Aldrin, oxygen is go. Water is flowing. Com check. Armstrong spoke into his helmet microphone, Houston, tranquility. Radio check. Duke, tranquility, Houston. We read you loud and clear. Armstrong, Roger. The communication system was working. The PLSS was functioning. Armstrong was ready. Now it was Aldrin's turn. The entire process took over an hour. Each movement was slow, deliberate, verified. There were no shortcuts in space. Haste led to mistakes, and mistakes led to death. Before they could open the hatch and climb outside, they had to depressurize the lunar module's cabin. The interior was pressurized to approximately 5 pounds per square inch, enough to keep them alive but low enough to allow them to move in their spacesuits. The moon's surface had no atmosphere, a perfect vacuum. Opening the hatch without depressurizing would blow the air out explosively, possibly damaging equipment and certainly making it impossible to control the hatch. Aldrin opened the dump valve, allowing the cabin air to vent into space. The process was slow, taking several minutes. They listened to the hiss of escaping air, watched the pressure gauge drop, and waited. As the pressure decreased, the cabin became completely silent. Sound requires air to propagate, and without air, there was nothing to carry vibrations. The only sounds they could hear now were transmitted through the metal of the spacecraft itself, or through their helmet radios. Aldrin, okay. We're at zero cabin pressure. Armstrong, Roger. Opening the hatch. The hatch was not a normal door. It opened inward, which meant Armstrong had to carefully pull it toward himself, threading it past his bulky spacesuit and PLSS backpack. The hatch was small, barely large enough for a suited astronaut to fit through, and the process was awkward. Armstrong, okay. The hatch is coming open. Finally, the hatch was fully open. For the first time since landing, the interior of the lunar module was exposed directly to the moon's vacuum. Armstrong could see outside, the stark gray surface, the black sky, the sunlight unfiltered by any atmosphere. He knelt down and began backing out of the hatch, searching for the ladder with his feet. The ladder was attached to the side of the lunar module, a simple 9-rung ladder leading from the hatch to the landing pad. Armstrong descended slowly, 1 rung at a time, calling out his progress. Armstrong, okay. I'm going to step off the LM now. He was on the lowest rung, the porch, a small platform just above the ladder. From here, he would drop to the landing pad, then step onto the moon. But first, he pulled a lanyard that deployed the modular equipment stowage assembly, or MESA, a storage compartment on the side of the descent stage. The MESA contained tools, sample bags, and most importantly, a television camera that would broadcast the moonwalk to Earth. Armstrong, okay. Houston, I'm on the porch. Duke, Roger, Neil. Armstrong paused. He looked down at the surface, considering the final step. The landing pad was about 3 feet above the lunar surface. He would have to drop down, then take the first step. He said, I'm at the foot of the ladder. The LM footpads are only depressed in the surface about 1 or 2 inches. The surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. Now and then, it's very fine. He was describing what he saw, providing data for the scientists and engineers on Earth. Then he prepared to step off. Armstrong, I'm going to step off the LM now. He lifted his left foot from the pad and placed it onto the moon's surface. Then he brought his right foot down. Armstrong, that's one small step for man, one giant leap for mankind. The words were transmitted back to Earth, heard by millions of people watching on television, listening on radios. The step was taken at 2:56 Universal Time Coordinated on July 21, 1969, 6 hours and 39 minutes after landing. Armstrong had become the first human being to walk on another world. Armstrong's first actions were methodical. He tested his mobility, moving his arms and legs, kicking at the dust, checking how his boots interacted with the surface. Armstrong, the surface is fine and powdery. I can pick it up loosely with my toe. It does adhere in fine layers like powdered charcoal to the sole and sides of my boots. I only go in a small fraction of an inch, maybe an eighth of an inch. But I can see the footprints of my boots and the treads in the fine sandy particles. Each observation was important. The engineers needed to know if the surface was stable, if the dust posed any risks, if the astronauts could move effectively. Armstrong moved away from the ladder, testing his balance in the moon's 1/6 gravity. He found that he could move easily, almost bouncing with each step. Armstrong, there seems to be no difficulty in moving around as we suspected. It's even perhaps easier than the simulations at 1/6 g that we performed on the ground. He collected a contingency sample, a small bag of lunar soil scooped up quickly and stored in his suit pocket. This sample was the minimum acceptable return. If the EVA had to be aborted immediately, at least they would bring back some moon rocks. Then Aldrin began his descent down the ladder. Armstrong guided him, providing tips on how to navigate the narrow hatch and the ladder rungs. Aldrin, okay. Now I want to back up and partially close the hatch, making sure not to lock it on my way out. He did not want to lock himself outside. That would be a very short moonwalk. Aldrin descended the ladder and joined Armstrong on the surface. Aldrin, beautiful view. Armstrong, isn't that something? Magnificent sight out here. Aldrin looked around, taking in the scene. Then he offered his own famous assessment. Aldrin, magnificent desolation. Those two words captured the contradictions of the moon, beautiful yet lifeless, inspiring yet barren. It was a place of extremes, a world untouched by wind or water, where everything was sharp edges and stark contrasts. Now that we have followed the descent, landing, and first steps, let us step back and consider what the transcript reveals about the interaction between humans and machines. The Apollo guidance computer was, in many ways, the unsung hero of the mission. It performed billions of calculations, controlled the descent engine, maintained the spacecraft orientation, and displayed information to the crew, all with less computing power than a modern car key fob. But the computer was not infallible. The 1202 and 1201 alarms revealed a design oversight. The rendezvous radar data was overloading the executive software. This was not a failure of the computer itself, but a failure of the humans who had programmed it and designed the procedures. They had not anticipated that particular combination of radar modes and descent phases. Yet the system worked anyway. The computer detected its own overload, prioritized tasks, and continued flying. It did not crash. It did not give up. It simply informed the crew that it was busy, then kept working. And the crew, rather than panicking, trusted Mission Control's judgment. When Houston said go, they went. That trust was built on years of training, thousands of hours in simulators, and absolute confidence in the engineers who had designed the systems. The alarms also highlighted the importance of the human element. Jack Garman, a young engineer who had studied alarm codes obsessively, knew instantly what 1202 meant. He had run simulations, tested failure modes, and prepared for exactly this kind of situation. When the alarm occurred during the real mission, he was ready. He made the call, and his call saved the mission. This is the essence of successful space exploration, combining machine precision with human judgment. The computer could fly the descent trajectory more accurately than any human pilot, but it could not recognize a boulder field and decide to fly somewhere else. Armstrong could see the danger and take control, but he relied on the computer to maintain descent rate and keep the spacecraft stable while he searched for a landing site. Neither could have succeeded alone. Fuel margins, how close was it? The question that dominated public imagination after Apollo 11, the question that still fascinates people today, is deceptively simple: how close did they come to running out of fuel? The answer, as with so many things in Apollo, is both technically complex and somewhat controversial, involving careful analysis of fuel consumption rates, gauge calibration errors, and the definitions of what constitutes running out in a spacecraft context. When Charlie Duke made the 60 seconds call-out, he was not saying there were literally 60 seconds of fuel remaining in the descent stage tanks. He was not measuring time until the engine would sputter and die, leaving them in free fall with no thrust to slow their descent. The call-out had a more specific, more technical meaning: 60 seconds until they reached what was called bingo fuel, the point at which they would have to either land immediately or abort, with no middle ground, no possibility of continuing to search for a better landing site. Bingo fuel was calculated to ensure that if they aborted at that moment, they would have enough propellant to fire the ascent engine, separate from the descent stage, reach a stable orbit, and rendezvous with Columbia. Aborting required significant fuel because the ascent stage would have to accelerate rapidly, climbing away from the surface, establishing an orbit that would intersect with Collins's trajectory. If they continued past bingo without landing, an abort might not have enough fuel to reach orbit safely, leaving them in an unstable trajectory, perhaps reaching orbital velocity but not the right orbit, perhaps missing the rendezvous, perhaps running out of fuel before completing the climb. So the 60-second call-out was really a warning: you have 60 seconds to decide whether to land or abort. If you have not landed by the time those 60 seconds expire, you must abort. There is no third option. There is no hovering and thinking about it. Land or abort, those are your choices, and you have 1 minute to make that choice. Armstrong, of course, did not abort. He continued searching for a landing site, continued flying horizontally, continued descending slowly, burning fuel at a rate of approximately 2 pounds per second. When he finally landed, more than 60 seconds had passed since Duke's call-out. He had violated the bingo fuel rule, had continued past the point where Mission Control had said he must either land or abort. Why did Mission Control not force an abort? Why did they allow Armstrong to continue? The answer lies in the uncertainty inherent in the fuel measurement system. The descent stage fuel was stored in 4 tanks, 2 containing fuel and 2 containing oxidizer. The amount of propellant remaining was measured using sensors that detected pressure and temperature in the tanks. Those measurements were fed into equations that calculated the mass of propellant based on the ideal gas law and the properties of the specific chemicals being used. The calculations were reasonably accurate, but they were not perfect. They included safety margins, conservative assumptions that erred on the side of caution. In reality, there was more fuel available than the gauges indicated. The sensors measured the pressure in the ullage space, the gas-filled void at the top of each tank. As propellant was consumed, that void expanded, and the pressure dropped. But the pressure drop was not perfectly linear with propellant consumption because the tanks were not perfectly uniform, because the propellants did not behave exactly like ideal gases, because temperature variations created measurement errors. The fuel quantity indication system was designed conservatively, to indicate slightly less fuel than was actually available, to ensure that any measurement error would not lead to a situation where the crew thought they had fuel when they actually did not. Post-mission analysis, conducted after Armstrong and Aldrin were safely back on Earth, after engineers had time to review all the telemetry data and reconstruct the descent trajectory in detail, showed that when Eagle landed, there were approximately 216 pounds of usable propellant remaining. At the descent engine's throttle setting during the final seconds, that represented approximately 45 to 50 seconds of hover time, not the 25 seconds suggested by the conservative interpretation of the 60-second call-out. 50 seconds. That is a more comfortable margin, but it is still terrifyingly small. If Armstrong had needed to fly another 100 feet, if the terrain had required more searching, if he had hesitated or misjudged the descent rate, they would have run out of fuel before landing, and they would have been forced to abort at extremely low altitude with a very uncertain probability of success. An abort at low altitude would have been one of the most dangerous maneuvers imaginable. The procedure called for Armstrong to hit the abort stage button, which would fire explosive bolts separating the ascent stage from the descent stage, and simultaneously ignite the ascent engine at full thrust. The ascent engine produced 3,500 pounds of thrust, enough to accelerate the ascent stage rapidly upward, away from the surface. But if they were very close to the ground when the abort occurred, the ascent engine's exhaust would strike the surface and reflect back toward the spacecraft, creating a complex, turbulent flow field that could destabilize the vehicle or damage the engine bell. Additionally, the descent stage would be left behind, sitting on its engine bell if they aborted after touchdown or crashing to the surface if they aborted while still airborne. If the descent stage fuel tanks ruptured on impact, hypergolic propellants could spray across the landing area, creating a toxic cloud that would contaminate the region. The ascent stage would be climbing through that cloud, potentially exposing its engine to corrosive chemicals. And there was the psychological factor. Aborting after coming so close to landing, after surviving the descent and the alarms and the fuel warnings, would have been a devastating emotional blow. Armstrong and Aldrin had trained for years for this mission. The entire nation was watching. The pressure to succeed was immense, perhaps stronger than any rational analysis of risk could fully account for. Armstrong's decision to continue past bingo fuel was not just a technical calculation. It was a bet that he could find a landing site in time, a bet that the fuel gauges were conservative, a bet that the mission was worth the risk. He won that bet. But it was close. Very close. And if the situation had been slightly different, if the boulder field had extended farther, if the safe area had been another 50 feet beyond where he landed, we might be telling a very different story today. The fuel issue became a subject of intense study after Apollo 11. Engineers analyzed the descent trajectory, the fuel consumption, the gauge accuracy. They refined the propellant measurement systems for later missions. They adjusted the abort procedures, giving commanders slightly more discretion, slightly more time to make the landing decision. They also improved the landing site selection process, using better photography, better terrain analysis, better predictions of where boulders and craters might be hidden. Apollo 12, the second lunar landing mission, benefited from these improvements. Pete Conrad landed with more fuel remaining, partly because of better trajectory planning, partly because of better fuel management, and partly because of luck. Apollo 12's landing site was safer, flatter, less cluttered with obstacles. Conrad could trust the computer's trajectory more, could take manual control later, could spend less time searching. But even with improvements, every lunar landing was a fuel-limited operation. The descent stage could only carry so much propellant, and every pound of fuel was a pound that could not be scientific equipment or lunar samples. The spacecraft was always operating at the edge of its capabilities, always pushing the limits of what was possible. That was the nature of Apollo, the nature of exploration in an era before reusable spacecraft or in situ propellant production. You had one chance, one fuel load, one opportunity to land. And you had to make it work. Armstrong made it work. He landed with enough fuel to spare, but not much. He pushed the margins farther than anyone had anticipated, but not beyond what the spacecraft could handle. He made a decision in the moment, under pressure, with incomplete information, and he made the right decision. That is leadership. That is skill. That is the kind of judgment that no simulation can fully train, no checklist can fully prescribe. You can prepare for it, you can practice scenarios that develop the relevant mental muscles, but ultimately, in the moment of truth, you have to trust your instincts, your training, your feel for the machine, and your understanding of what is possible. Armstrong had that trust, that feel, that understanding. And because he did, humanity walked on the moon. Trajectory analysis. Where did they land? The descent trajectory was supposed to bring Eagle to a specific landing site in the Sea of Tranquility, a location chosen for its flatness and lack of obstacles. But Armstrong landed for miles downrange from that target. Why? Several factors contributed to the deviation. First, the initial lunar orbit was not perfectly circular. Slight errors in the orbit insertion burn meant Eagle's starting altitude was slightly different than planned. Second, the Moon's gravity field is uneven, distorted by concentrations of mass beneath the surface called mascons. These mass concentrations pulled on the spacecraft in unpredictable ways, altering its trajectory. Third, the computer's inertial navigation system, while accurate, accumulated small errors over time. And fourth, Armstrong's manual flying added additional horizontal distance. Each of these errors was small individually, but they compounded. The result was that when Armstrong finally landed, Eagle was miles from the planned site. But this was not a failure. The mission planners had anticipated trajectory dispersions. They had chosen a large, relatively flat landing zone precisely because they knew the spacecraft might not land at the exact target. The important thing was to land safely somewhere in the zone, not to hit a specific coordinate. Armstrong's landing site, later named Tranquility Base, was safe. The terrain was rough, but not dangerous. The lunar module was stable. The mission could continue. In later Apollo missions, trajectory accuracy improved. Apollo 12 landed within walking distance of the Surveyor 3 probe, demonstrating pinpoint landing capability. But on Apollo 11, simply landing anywhere safely was achievement enough. One aspect of the transcript that is easy to overlook is the communication delay. Radio signals travel at the speed of light, but even at that incredible speed, the 250,000-mile distance between Earth and Moon introduced a noticeable lag. When Armstrong said something, it took 1.3 seconds for his words to reach mission control. When Houston replied, another 1.3 seconds passed before Armstrong heard the response. This 2.6-second round-trip delay meant that real-time conversation was impossible. Every exchange was slightly out of sync, every question answered seconds after it was asked. This delay added to the stress of the descent. When the 12:02 alarm triggered, Armstrong and Aldrin had to wait precious seconds for Houston's response. In that time, they were falling toward the Moon, the situation evolving, the altitude decreasing. They could not stop and wait for guidance. They had to keep flying, keep reading instruments, keep making decisions. The controllers in Houston faced the same problem in reverse. They could see telemetry showing the spacecraft status, but that data was already 1.3 seconds old by the time it reached them. They were always looking at the past, trying to predict the future, making calls based on information that was already obsolete. This is one of the fundamental challenges of space exploration. The farther you go, the longer the communication delay. When humans eventually travel to Mars, the delay will be measured in minutes, not seconds. Real-time support from Earth will be impossible. The crew will be truly alone, forced to make decisions without consulting mission control, relying on their own training and judgment. Apollo 11 was a preview of that future. It demonstrated that humans could operate effectively with communication delays, that they could make critical decisions quickly, and that they could trust their training even when help was seconds away but felt like miles. The software running on the Apollo guidance computer during the descent was called Luminary 1A. It was written in a low-level assembly language by a team of programmers at MIT's Instrumentation Laboratory, led by Margaret Hamilton. The code was remarkable for its efficiency and reliability. Every byte of memory was precious, so the programmers used tricks to save space, reusing code, packing multiple flags into single words, optimizing algorithms to minimize execution time. The result was a program that could navigate to the moon, control a rocket engine, display information, and handle errors, all within the constraints of 1960s computing. But Luminary 1A had the radar bug. The rendezvous radar data overload that caused the 1202 and 1201 alarms was a flaw in the software architecture. The executive scheduler did not anticipate that particular workload, and it became overwhelmed. After Apollo 11, the software was revised. Luminary 1B, used on subsequent missions, included fixes to prevent the radar overload. The executive scheduler was optimized, priorities were adjusted, and additional safeguards were added. But the fact that Luminary 1A worked despite the bug is a testament to the robustness of the design. The computer did not crash. It did not freeze. It raised an alarm, continued with critical tasks, and waited for human judgment. That graceful degradation, the ability to handle unexpected problems without catastrophic failure, is the mark of good software engineering. Today, the Luminary source code is available online, preserved as a historical artifact. Programmers study it, learning from the techniques used to write reliable software under extreme constraints. The code is a reminder that computing is not just about speed or capacity, but about correctness and resilience. While Armstrong and Aldrin receive most of the historical attention, the flight controllers in mission control were equally essential to the mission's success. Each controller was an expert in their domain, monitoring specific systems, making split-second decisions, and coordinating with the flight director. Steve Bales, the guidance officer, was only 26 years old during Apollo 11. When the 1202 alarm occurred, he had to decide in seconds whether to abort or continue. He consulted Jack Garman, trusted the analysis, and made the call, go. That decision required not only technical knowledge but also courage. If he was wrong, he would be responsible for the deaths of 2 astronauts. Gene Kranz, the flight director, was the leader of the team. He made the final go-no-go calls, coordinated the controllers, and maintained order in a room filled with stress and uncertainty. His leadership style was direct and demanding. He expected excellence, and he got it. Charlie Duke, the Capcom, was the voice of mission control. He spoke to the crew, relaying information, asking questions, providing reassurance. His job required clarity and calm, even when the situation was anything but calm. And there were dozens of others, trajectory specialists, systems engineers, flight surgeons, communication technicians, each playing a critical role. They worked 12-hour shifts, sleeping little, studying telemetry, running simulations, preparing for every possible contingency. Mission control was not a building or a room. It was a team, a collective intelligence greater than any individual. And on July 20, 1969, that team performed flawlessly. It is worth considering how close Apollo 11 came to failure, and what might have happened if certain events had unfolded differently. If the 1202 alarm had been caused by a more serious problem, Houston might have called for an abort. The ascent stage engine would have fired, separating from the descent stage, and Eagle would have climbed back to orbit without landing. The mission would have been a failure, but the crew would have survived. If Armstrong had not taken manual control, the computer would have flown Eagle into the boulder field. The spacecraft might have tipped over on landing, damaging the ascent stage and stranding the crew. Or it might have crashed, killing them instantly. If the fuel had run out before Armstrong found a landing site, he would have been forced to abort at very low altitude. The ascent stage engine would have fired with the descent stage still attached, creating a dangerous, unstable situation. The spacecraft might have survived, but it would have been a close thing. If the landing gear had failed to deploy, or if it had been damaged during descent, the spacecraft would have crashed. There was no backup landing system. If the ascent stage engine had failed to ignite after the moonwalk, Armstrong and Aldrin would have been stranded. There was no rescue capability. They would have had perhaps 2 days of life support before the oxygen ran out. Any one of these scenarios would have changed history. Apollo 11 would be remembered as a tragedy, not a triumph. The space race might have ended differently. Public support for NASA might have evaporated. But none of these things happened. Through a combination of good design, thorough testing, skilled flying, and luck, everything worked. The mission succeeded. And that success was not inevitable. It was earned. While Armstrong and Aldrin were descending to the moon, approximately 600 million people were watching on television, listening on radios, or following the mission through newspapers. It was, at the time, the largest audience for a single event in human history. In the United States, families gathered around televisions, staying up late to watch the moonwalk. In Europe, it was early morning, but people woke up to witness history. In the Soviet Union, where the government had downplayed the American space program, citizens listened to bootleg radio broadcasts, eager for news. The descent itself was tense for the audience. The television networks broadcast Mission Control's audio feed, so viewers heard the same call-outs and alarms that the astronauts heard. They heard the 60-second fuel call. They heard the silence after landing. They heard the Eagle has landed. And they erupted in celebration. In homes, bars, public squares, people cheered, cried, embraced. It was a moment of collective joy, a rare instant when the entire human species felt united in achievement. President Richard Nixon watched from the White House. He had prepared 2 speeches, one for success and one for failure. He used the success speech, calling Armstrong and Aldrin from the Oval Office to congratulate them while they were still on the moon. The Soviet Union's reaction was more muted publicly, but privately, Soviet space engineers and cosmonauts recognized the achievement. They knew how difficult it was, how many things could have gone wrong. Some felt admiration. Others felt envy. But all understood that America had won the race to the moon. The descent transcript is more than a historical document gathering dust in NASA archives. It is more than a curiosity for space enthusiasts or a teaching tool for engineering students. It is a blueprint for how humans and machines can work together under the most extreme conditions imaginable, a demonstration of what becomes possible when preparation meets opportunity, when courage meets calculation, when trust meets technical excellence. The transcript demonstrates the value of preparation in its purest form. Armstrong and Aldrin spent hundreds of hours in simulators, practicing the descent over and over, memorizing every call-out, learning to interpret every number, training their minds and bodies to respond correctly even under extreme stress. They practiced normal descents until they could fly them perfectly in their sleep. Then they practiced abnormal descents, descents where engines failed, where computers crashed, where fuel leaked, where every imaginable disaster occurred. They trained until their responses became automatic, until thinking was replaced by doing, until the correct action flowed naturally from the situation without conscious deliberation. That training saved the mission. When the 12:02 alarm occurred, Armstrong and Aldrin did not freeze. They did not panic. They called it out, waited for Houston's response, and continued flying. When Armstrong decided to take manual control, he did not hesitate or second-guess himself. He moved the controller, flew the spacecraft, searched for a landing site, made decisions in fractions of seconds because he had made similar decisions hundreds of times before in the simulator. The motions were familiar. The interface was known. The responses were practiced. The transcript also demonstrates the importance of trust that spans multiple levels and multiple directions. Armstrong and Aldrin trusted the engineers who had designed the spacecraft, who had calculated the descent trajectory, who had written the software. They trusted that the years of design reviews and testing and analysis had produced systems that would work, that would not fail at the critical moment. That trust was not blind faith. It was earned through rigorous engineering, through transparency, through a culture that valued finding and fixing problems rather than hiding them. The crew trusted mission control, trusted that the flight controllers monitoring telemetry knew what they were talking about, that when Houston said go on the 12:02 alarm it meant they had analyzed the situation and determined it was safe to continue. That trust was reciprocal. Mission control trusted the crew to fly the spacecraft correctly, to make good decisions, to report problems honestly. There was no room for ego or pride. If something was wrong, you said it immediately, clearly, without euphemism or evasion. And perhaps most importantly, Armstrong and Aldrin trusted each other. They had been training together for months, learning each other's rhythms, understanding how the other thought and reacted. During the descent, Aldrin provided Armstrong with exactly the information he needed, exactly when he needed it, without being asked. He called out altitude and descent rate in a steady rhythm that kept Armstrong informed without overwhelming him with data. He monitored systems, managed the computer, cross-checked readings, all while Armstrong focused on flying. It was a partnership built on mutual respect and shared purpose, and neither man could have succeeded alone. The lessons learned from Apollo 11 informed every subsequent space mission. The software was improved, with the rendezvous radar issue fixed to prevent the executive overflow alarms. The landing procedures were refined, with better trajectory planning to account for the moon's uneven gravity. The training was enhanced, with even more emphasis on manual flying and decision-making under pressure. Engineers studied the 12:02 alarm, the trajectory errors, the fuel margins, the manual takeover, and they made changes to prevent similar problems on future missions. But Apollo 11 also revealed fundamental truths that remain relevant today, truths that apply not just to space exploration but to any endeavor where stakes are high and margins are thin. Space is unforgiving. Mistakes are fatal. Success requires not just technology, but wisdom, courage, and teamwork. You cannot rely on technology alone, because technology will eventually encounter situations its designers did not anticipate. You cannot rely on human skill alone, because humans make mistakes when stressed or fatigued. But when humans and machines work together, each compensating for the other's weaknesses, each amplifying the other's strengths, impossible things become possible. The transcript reminds us that exploration is not about grand gestures or heroic speeches. It is not about flags and footprints, though those have their place. It is about doing the work, reading the instruments, making the calls, trusting the people around you. It is about altitude callouts and program alarms and fuel quantities. It is about the small, precise steps that accumulate into giant leaps. It is about showing up prepared, doing your job correctly, and trusting your teammates to do theirs. Armstrong's manual takeover during the descent is often cited as an example of human superiority over machines, as proof that computers cannot be trusted for critical tasks, that human judgment will always be necessary. But that interpretation misses the deeper point. Armstrong could only take control because the computer maintained stability while he flew horizontally. The computer kept the descent rate correct, kept the spacecraft upright, managed the engine thrust, all while Armstrong focused on navigating around the boulder field. Without the computer, Armstrong would have had to control thrust, attitude, and position simultaneously, a task that would have overwhelmed even the most skilled pilot. The computer could only guide them close to the target because Armstrong recognized that the terrain was wrong and intervened. The computer was following its programmed trajectory perfectly, doing exactly what it had been told to do. But it had no eyes, no understanding of boulders or craters or safe landing zones. It could only follow the mathematics, and sometimes mathematics alone is not enough. It was not human versus machine. It was not a competition or a conflict. It was human and machine working together, each doing what it did best, each trusting the other to fulfill its role. That partnership, that collaboration between carbon and silicon, between intuition and calculation, between judgment and precision, is what made the landing possible. And that partnership is the template for our future. As we develop more sophisticated artificial intelligence, more autonomous systems, more capable machines, the lesson of Apollo 11 remains vital. Do not design machines to replace humans, design machines to work with humans. Create systems that amplify human capabilities rather than attempting to eliminate human involvement. Build interfaces that allow humans to understand what machines are doing, to intervene when necessary, to provide judgment and context that no algorithm can replicate. The Apollo guidance computer was not trying to replace Armstrong. It was trying to help him, to handle the mathematics and the rapid-fire calculations so he could focus on the bigger picture. When he took control, the computer did not fight him or protest. It simply shifted modes, providing stability and automation for the tasks he was not actively controlling. That seamless transition between automation and manual control, that smooth handoff of authority from machine to human, is the ideal we should strive for in every system we design. The transcript also teaches us about communication, about the importance of clear, concise language when lives are at stake. Every word spoken during the descent was chosen carefully, stripped of ambiguity, designed to convey maximum information with minimum syllables. 60 seconds was not elaborated into "you have 60 seconds of fuel remaining before you must abort." The meaning was understood implicitly, and wasting time with unnecessary words could have cost precious seconds that they did not have. This economy of language required training, required that everyone involved speak the same technical dialect, understand the same jargon, interpret phrases the same way. A go from Houston did not mean maybe or probably or we think so. It meant go, continue, proceed, you have permission and support and confidence from everyone monitoring this mission. A no-go would have meant abort immediately, no questions, no appeals. That clarity, that precision, that shared vocabulary eliminated confusion and enabled rapid decision-making. The transcript shows us the value of procedure, of checklists, of systematic approaches to complex tasks. Every major action during the descent followed a checklist, a sequence of steps designed by engineers and tested in simulators, proven to work if followed correctly. The checklists were not busywork or bureaucracy. They were memory aids, ensuring that in the stress of a critical moment, nothing was forgotten, no step was skipped, no switch was left in the wrong position. But the transcript also shows the limits of procedure, the moments when the checklist does not cover the situation, when human judgment must take over. Armstrong's decision to take manual control was not in the checklist. The flight plan did not say if you see boulders, fly somewhere else. It assumed the landing site would be safe, that the computer's target would be acceptable. When that assumption proved false, Armstrong had to improvise, had to use his training and experience to make a decision that was not scripted, that required understanding the situation and responding appropriately. That balance between following procedure and knowing when to deviate is the mark of expertise, the difference between competence and excellence. Anyone can follow a checklist. But recognizing when the checklist is insufficient, when the situation requires adaptation, when rigidity will lead to disaster and flexibility will lead to success, that requires judgment that cannot be reduced to rules, that can only come from experience and training and a deep understanding of the systems involved. The Apollo 11 descent transcript captures all of this in 13 minutes of audio, in the spare, technical language of professionals doing their jobs. It is not dramatic in the way movies are dramatic, with soaring music and emotional speeches. It is dramatic in the way reality is dramatic, with stakes that need no embellishment, with tension that needs no soundtrack, with human beings facing genuine danger and emerging victorious through skill and preparation and a little bit of luck. When we read the transcript today, more than 5 decades after the events it records, we are reading the words of people who changed the course of human history. But they did not see themselves that way in the moment. They saw themselves as engineers and pilots and flight controllers doing their jobs, working through problems, making decisions based on data and training. The history would come later. The recognition would come later. In the moment, there was only the work, the numbers, the spacecraft falling toward the moon, and the absolute necessity of getting everything right because there would be no second chance. That is the real lesson of Apollo 11, the truth that echoes through every line of the transcript. Excellence is not about grand gestures or individual genius. It is about teams of skilled people working together toward a common goal, supporting each other, trusting each other, doing their jobs with precision and care and dedication. It is about preparation and practice and learning from failures. It is about building systems that work, testing them until you are confident they will not fail, and then trusting them when it matters most. The transcript is a monument to that kind of excellence, to that kind of teamwork, to that kind of dedication. It deserves to be studied, to be remembered, to be celebrated not just for what it represents but for what it teaches. Every word matters. Every number means something. Every voice belongs to a person who gave years of their life to making this moment possible. When Armstrong said the Eagle has landed, he was speaking for himself and Aldrin, but he was also speaking for the thousands of people who had built the spacecraft, written the software, calculated the trajectories, trained the crew, monitored the systems, supported the mission. He was speaking for a nation that had committed itself to an impossible goal and achieved it through determination and skill and sacrifice. That is what the transcript represents. That is what it means. And that is why, decades after the events it records, people still study it, still read it, still find inspiration in its spare technical language and its 13 minutes of controlled tension resolving into triumph. As of this recording, more than 5 decades have passed since Apollo 11. 12 humans have walked on the moon, all between 1969 and 1972. Then we stopped going. The reasons are complex: budget cuts, political priorities, public apathy, risk aversion. But the capability to return remains. The knowledge has not been lost. The engineers who built Apollo are mostly gone, but they left behind documentation, blueprints, code, and most importantly, the transcript of what they did and how they did it. Today, new programs are underway to return humans to the moon. NASA's Artemis program plans to land astronauts on the lunar surface in the coming years. Private companies are developing their own lunar landers. Other nations, including China and India, are pursuing robotic and human missions. When the next astronauts descend to the moon, they will use computers millions of times more powerful than the AGC. They will have high-definition cameras, real-time communication, advanced navigation systems. The technology will be vastly superior. But the fundamentals will be the same. They will still have to manage fuel. They will still have to navigate to a safe landing site. They will still have to trust their machines and their training. And they will still feel the same exhilaration and fear that Armstrong and Aldrin felt as they dropped toward an alien surface, knowing that every second mattered, that every decision could mean life or death. The Apollo 11 descent transcript will serve as a guide and inspiration for those future crews. It will remind them that humans have done this before, that the impossible can become routine with enough preparation and courage. And perhaps, decades from now, someone will record a new transcript, reading the words spoken by astronauts descending to Mars, or an asteroid, or some destination we have not yet imagined. And they will look back at Apollo 11 as the beginning, the moment when humanity proved it could leave its cradle and reach for the stars. We have journeyed together through the Apollo 11 descent, reading the transcript word by word, number by number. We have heard the altitude callouts, the alarms, the moment of landing. We have explored what those words reveal about technology, training, and trust. But the real power of the transcript lies in its simplicity. It is not a dramatic narrative. It is not poetry. It is simply the record of people doing their jobs under incredible pressure, speaking clearly and precisely because precision was the only thing that mattered. In our daily lives, we rarely face such stark choices. Our mistakes are usually forgivable. We have time to reconsider, to try again. But for Armstrong and Aldrin, and for the controllers in Houston, there was no second chance. They had one opportunity to get it right, and they did. That is the lesson of Apollo 11. Not that technology can solve any problem, or that humans are inherently heroic, but that careful preparation, clear communication, and trust in each other can overcome extraordinary challenges. When you look up at the moon tonight, remember that humans have walked there. Remember that they flew through the void, descended through alarms and uncertainty, and stepped onto another world. And remember that they did it not through magic, but through math, through engineering, through the simple act of reading numbers from a display and trusting those numbers to be true. That is exploration. That is achievement. That is what we are capable of when we work together, trust each other, and dare to do what has never been done before. Thank you for joining me on this journey through the Apollo 11 descent transcript. If you enjoyed this exploration, please take a moment to like this video, subscribe to Sleep Orion, and share your thoughts in the comments. Your support helps these stories reach others who find wonder in the details of human exploration. Until next time, sleep well, dream of distant worlds, and remember, the moon is not so far away. Humans have been there. And one day, we will return. Good night, and safe travels through the cosmos.